And now we're going to take a look at 2.03 graph rational functions. Rational functions are something we looked at in 2.02. Those were specifically called reciprocal power functions because they had the variable of x in the denominator of a fraction. And yes, you will see that again today, but now we're going to look at transformations, which has to do with our first goal, describe the effect a given parameter has on the graph. We know that means there are transformations happening. Something will be changing with our graphs. Determine the domain. Okay, you've had some good practice on that as well in 2.02. So you should be set up pretty nicely for that. But we also want to be able to find the zeros, the range, and equations of the asymptotes. And finally, be able to graph these rational functions in an equation in this form. So this is something you will see many times today. Write it down now or on the next page. But this is our parent rational function with all possible transformations. So what is a rational function? Well, it's a function in the form of a fraction with a polynomial in the numerator and denominator. The general form, again, we see it here. And you might be wondering, okay, a rational function has a polynomial in the numerator and denominator. Isn't that pretty much any fraction? Not quite, because there are situations where a term is not a polynomial. So let's read about that. An expression with a polynomial that is not a polynomial is one that contains negative exponents, fractional exponents, variables in the denominator, or variables under a radical sign. So essentially, any expression where the variable's exponent is not a whole positive number, well, that's not considered a polynomial. And you might be thinking, wait a second, this said a polynomial can't have variables in the denominator, and I see variables in the denominator. But read it carefully. What it's really saying is the denominator itself, well, let's start with the numerator. The numerator itself can't have any of those things. So we're viewing them separately, and that's true. The numerator for the problems we'll see today will not fit any of these requirements that make it not a polynomial, and then you view the denominator as its own separate entity. This also is a polynomial. So what are we really doing with these today? Well, you know there's transformations, but the only real difference between 2.02 and what you're learning right now is that the vertical and horizontal asymptotes are going to shift. It's time to move them around. Okay? So hopefully you remember for any parent function that is a rational function, there is a horizontal asymptote right on the x-axis. That line is y equals 0. Okay? Because keep in mind, we will talk about these asymptotes moving around, but we haven't yet. So let's just go off what we know already, and we know it's right there. You also learned what happens when the function is negative. This is a refresher. If the function is negative, it is reflected over that horizontal asymptote, this dashed line right here. So this becomes a mirror. And we started with this parent function with no transformations. That's the red line here and there. Remember, this one function gives you both of those lines. But if it's negative, we have our mirror right here at y equals 0, and the red line flips over to become the blue line, and this red line flips up to become this blue line. So the red lines give us our original positive parent function we see here, and the blue lines are the negative transformation of that. Okay, what else? Well, the numerator a, that is also something we talked about in our previous lesson, but let's visit it again. Okay, and when we're looking at a, we're really looking at the positive number value. Okay, so we want to take the absolute value of whatever you see. If it's 1 and there's a negative sign, you want to just take it as 1. If this had a negative in front, you want to just view a as 3, and so on. Okay, so what happens? Well, let's take a look at our graph. We have all three graphed here, starting with the basic parent function, just 1 over x. That's our blue lines here and there. Sometimes they're also called branches. Now, if a is 1, there's no vertical stretch or compression. It says it right here. That's the same as the parent function. That's what we see, again, with the blue lines. But what happens if a is now greater than 1? Well, that means there is a vertical stretch. That means you're grabbing the top and the bottom of your graph lines, and it has that rubber band effect where they're getting further apart, and we see that indicated with these green arrows, right? Stretching, pulling further away from that horizontal asymptote. So we see green line further up here, green line further down there, moving up and down in those vertical directions. And last but not least, for the numerator, if the absolute value of a is less than 1, like let's say 0.5, that is a vertical compression. We're still moving in an upward and downward motion, but it's exactly the opposite. So this red line is being compressed. All of the points are getting closer to that horizontal asymptote. Same thing here. Compression means squeezing together, and if it's vertical, it's in a upwards and downwards motion. So with green, we see a vertical stretch. With red, we see a vertical compression, and blue is where there are no stretches, vertical stretches or compressions. Now, before we move forward and start to really talk about the transformations and shifts of these asymptotes moving up, down, and side to side, we really need to be familiar with the position of the vertical and horizontal asymptotes of the parent rational functions. Here's some examples. This is a parent function, this is a parent function. There's no real transformations, just the powers are different, okay? And you have your handout from before. Hopefully you remember where positive and odd quadrants are, if it's positive and even, where those are. Okay, we're not really going to get into this because we're not so much worried about graphing this all the way, however that may look. Okay, we're more concerned with where are the horizontal and vertical asymptotes of the parent functions. And they are always here. We just saw that one, right? That's a horizontal line. And the equation on that line is y equals 0. And then we have our vertical asymptote here, right on the y-axis at x equals 0. So that's where they start, and that is super important to know because they're going to move, and we got to know where they're starting to know where they're going, right? Okay. And here are our main transformations that are new to us today. The first one is dishonest H. And I like to call him dishonest H because he's a sneaky guy. He's actually the opposite of what you see. So we see H right there, and let's learn about him. Dishonest H tells you the horizontal shift and vertical asymptote. It tells you both of those things. Because a vertical line, like this dash gray line here, can only move left and right? It doesn't move up and down because this line goes up forever and down forever. So we're not concerned about that. We care more about, is it moving left or right? Okay. And like I said, it's the opposite of what you see. So negative h, like -2 or -5, something like that, means you move right. That is the positive direction when it comes to x values. And if you see plus a number like 1, 2, or anything else, that actually means you move left in the negative direction on the x-axis. Meaning your domain will always look like this, where that h value is going to be here and there. That will be what you skip over. Remember, the parentheses mean that's not included. So let's just look at this original vertical asymptote, for example. We know and we can see that these red lines are never going to touch this vertical asymptote. That's what an asymptote is, right? It's a line your graph lines never touch or cross. So think about it. This red line is going left forever, and that's negative infinity. And it comes all the way up to this x value of 0, but we have no points on that line. So h in this case is 0. This is our parent function, the red lines I'm looking at first. And that's going to be united with, well, we see over here, this is going to pick up where we left off, just on the other side of the y-axis. So it will continue after 0 on forever in this positive direction. That's a refresher of why the domain looks like it does, but this is really helpful to us because look, this takes a lot of the guesswork away for you, right? All you have to do is find h and plug it in there and you are golden. So write this down. Always is a powerful word in math. Now, let's just look at everything that's happening. The red lines, like I mentioned, are the parent function. The blue lines are the transformed function. Notice the vertical asymptote moved from x equals 0. We see that here to the right, moved over to x equals 3. So this means the function of these blue lines must be f of x equals 1 over x minus 3. Okay? We're not really concerned about the 1. We're really concerned about this x minus 3. So if it shows a negative, that means we're moving in the positive direction when it comes to the x values. So we're moving 3 to the right, indicated by all these green arrows. And that's all you need to really know when it comes to moving this. But if you want to know why, well, think about it. Look at what we start with. We start with the denominator of x minus h, right? So if we have x minus 3, the question you're really asking yourself is, what did, that should not be a parentheses here, what did we have to put in here to get this? Well, 3, right? Because negative times positive is negative. Okay, that's why it's the opposite. Okay. All right, so what's the domain then? Can you figure it out? Well, we talked about a moment ago that you use this to your advantage. And what's h? What is h? Well, you see it right there, don't you? But remember, h is the opposite of what you see, right? So it's 3 and 3. Because we had to put in, remember, like this, we had to put in a 3. And that makes sense on our graph, right? You see the blue lines coming right up to, ooh, I put that at the wrong position, didn't I? Let's move this over. This should have moved all the way over to 3. Here we go. So 3, let's move this over. A little adjusting here. There we go. No, actually, okay, I see what happened. So I'm going to put this back where it was. What happened was I actually want this to be 2 to match my graph. There we go. Everything is in order. So now this should actually be 2. So now it will make sense. The blue lines go left forever all the way up until you get to 2, then skip over 2 and continue on forever. Okay. Now, can you identify the vertical asymptote here based off what you just learned? Well, you're hopefully seeing that it's right here. We can just visually see that. Vertical asymptote is x equals -2. Can you figure out what the function looks like? X, is it plus or minus? We moved in a negative direction, so it should look like a plus. But what actually is H? H is dishonest. It's the opposite of what you see, so H is -2. Okay? And the domain, if you're wondering, is going to look like this, where your H values go here and there. But my point is, the vertical asymptote could move to the right, but it could also move to the left. All right. But what about our other friend, elevator V? Well, we see that guy at the end of the function right here, and we call our friend elevator V because it moves just like an elevator. Imagine you're standing right here. Hey guys, you're at ground level, and whatever you see is what you get. It's a very straightforward value, okay? So if you move down 3, like you see here, you should expect V to be -3, okay? And that is absolutely true. So in this case, V is -3, okay? So if you're looking at your function, you'd have no changes to H here, but you'd have just -3 at the end. So the blue lines are the parent function, the orange lines are the transformed function. Okay, so we see that horizontal asymptote moving in a vertical direction. So there was a vertical shift 3 units down. Okay, we see our new function there. And can you identify the range? We've talked about domain, but what about the range? Well, range is all possible y values. So guess what? This affects the range. So this one, dishonest H, affects the domain, where elevator V affects the range. And it's always going to look like this for these rational functions. Very nice. So we already know we can set it up like this, right? Now we need to find V. Well, I pointed out just a moment ago that it's right there. So -3 and -3. And if we look at our graph, that makes total sense because we need all possible Y values of this orange line. Well, we know this goes down forever and it's going to come up just until you get before -3. It's going to skip over, so that's where the U for united comes in, and it's going to continue just on the other side of -3 and go up forever. Okay, so here's that negative infinity, the positive infinity, and here is that -3 that's not included. Again, the parentheses tell us that. Okay, we've looked at all the different types of transformations. Nothing new after this, but there's practice, and I need you to know that it is possible for all four transformations we've seen to happen in a single function. It won't happen every time. It won't happen most of the time, but it could. So let's start to practice after a quick heads up on graphing. Okay, here we see a function with our inputs. We're putting an x into this function. We see all those x values and we're getting our outputs, right? Great. We don't need to talk about that too much because my main point is when you're choosing your input values, which you will need to do to graph, you want to pick x values that are close to the intersection of your horizontal and vertical asymptotes, which is no longer at the origin always, right? Because we learned these lines can move around, okay? And here's why. If I plugged in, let's say 5, 6, 7, and I plugged in like -3, -4, -5, what part of the graph would I get? Well, I'd really only get like this kind of little flat part and this little flat part. If I only had those green parts of my lines graphed, would I have a good idea of what's going on? Probably not, right? Because we already know with these types of graphs, we're going to get these lines that get super close but never touch the asymptotes, right? But what we really care about is these points more in the middle. How much is it curving? Because remember, we had vertical stretches. It might come up more like this, right? Or we might have vertical compressions. It might go down like that, right? And of course, that would affect this side too. We really need to know where the curve is and how much it's curving. Okay, so my point is pick x values near the intersection there. So maybe 3, 4, 5, 1, 0, -1, things like that. So you get a good idea of where this curve is and how stretched or compressed it is, if at all. And with that said, it's time to answer several questions about this rational function. This will be a great chance for you to pause the recording and practice this, and then check it while I go through it. Let's do it. Okay, determine the asymptotes. So that has to do with dishonest H and elevator V, right? You pick whichever one you want to focus on first, but I see V clear as day is -3, and I like how transparent elevator V is. I know elevator V moves up and down, so I know it's a flat horizontal line, and that's right at -3. I'll use a different color so it's easier to see. Okay, so that is our horizontal asymptote at y equals -3. So notice if v is -3, then y is also -3. That's the equation of the line. This is the equation of, or the value that it's actually equal to in the function. Okay, so there was a transformation there, right? What about the vertical asymptote? Well, that has to do with dishonest h, right? Because it's a horizontal movement, left or right, so it's a vertical line. Dishonest h is the opposite of what you see. So if you see -2, h is +2. And if h is +2, the equation of the line is x equals +2. Let's put it on our graph. Vertical asymptote x equals 2. Okay, so what happened? The horizontal asymptote moved down 3 units because of the -3. The vertical asymptote moved right 2 units because of the -2. Okay, we have our asymptotes down. I'll get rid of these arrows so it's not too confusing because we need to do several more things. Okay, determine the domain and range. Well, didn't we just talk about that? We talked about domain being always like this, united with this. Same thing with range. It was set up very similarly. This, united with this, right? But what are those values? Well, domain went with H, right? And range went with V. So what is H? We see right there it's 2. And if you're ever unsure, you can always look at your graph. I'll do that after I fill in V. We see above V is -3. So there it is. You can always double check with your graph, okay? The x values, what's not included? Well, we can't have any points at 2. That makes sense. The range, we can't have any y values at -3, and we won't. That makes sense. Okay. We have a lot of helpful information, but we need to find some zeros, aka x and y intercepts. You remember how to do that? I hope so. To find x-intercepts, you set y equal to 0. Do you see y? Well, we know f of x is the same as y, right? So before I solve, let me just be clear on this. To find x-intercepts, you set y equal to 0. And to find y-intercepts, you set x equal to 0, right? Because any point on the x-axis, y is 0. And any point on the y-axis, x is 0, right? That's why that works out so nice, and let's do it. Easiest thing first. And we need that x out of the denominator, so we need to multiply both sides by that x minus 2. Because these will cancel out. You get 3 times x and 3 times -2. That looks like something we can definitely work with. That gives us 3x equals 7. Divide both sides by 3. X equals, since we're dealing with a graph, I'd like a decimal value. And I believe that's it. 7 divided by 3. Yes, yes. Okay, so what did we just find out? We found out when y is 0, x is 2.33. That is going to be about right there. Okay, we found an x-intercept. What about a y-intercept? Well, I don't have enough space, so if you need to pause, pause now, because I'm going to erase this. Okay, it's time to look at the y-intercept. Okay, so the y, we set x equal to 0 and solve for y. We get 0 minus 2. Well, that's going to give us -0.5. And this will give us -3.5 or -3.5. That was pretty quick and simple. So when X was 0, Y is negative 3.5. Just to make sure I steer you in the right direction, I'm going to quickly just check that I did that correctly. Moment. Where is that? There it is. And there we are, I think. Um, hmm, interesting. Yeah, 0, negative 3.5. Okay, good. So, 0, negative 3.5 right there. Okay, so we found this. We did this. We just found the zeros, and now we need to graph it. So finally, it's time to pick a few points, more points. We already have two to graph the rest of this. Okay, we know because of our horizontal and vertical asymptotes, we're going to have a line kind of like this, right? And kind of like this. But like I said a moment ago, we want it as accurate as possible. So we have 2 points. I would say get at least two more over here. I would probably pick x values of, I don't know, 3 and 4, let's say, and maybe for this line. So I'll do that first. So f of 3. So what do we get? 1 over 1 minus 3. That's 1 minus 3. That's negative 2. Okay, so when x was 3, y is negative 2. 3, negative 2. That looks like it fits into things, and that really gives us a key point down towards the intersection of those two lines, right? Okay, and this is going to go more or less like this, and then I'll try 4. 4, and that's 1/2 minus 3, so that should be negative 2.5. So 4, negative 2.5. That gets us really close to that line. I like, how did that happen? I like how close it is to that HA as well. Okay, let's do 2 more points over here and we will be done. Okay, I'm gonna go ahead and pick 1 and negative 1. So I'll start with negative 1. Negative 1 minus 2, there we go. We get 1 over negative 3 minus 3. What does that give us? 1/3 minus 3. That's negative 2.7 about. No, yeah, we'll just say 2.7. So we're looking for the point. Negative 1, negative 2.7. Does that fit what we're looking for? Negative 1. No, I did that incorrectly. That breaks our asymptote there. So, oh, negative 1, negative 2.7. No, that still doesn't fit it. So something went wrong. Let's see what it was. Let's double check. I picked negative 1. That should be 1 over negative 3. So here we go. Negative 0.33 minus 3, negative 3.33. Yeah, there was some sort of a computer miscalculation. 0.33, and that should be on our graph. Negative 1, there we go. And then positive 1 is the last thing we'll do. I'll just switch this to positive and we'll work it out. We get 1 minus 2, so we get negative 1 minus 3, or sorry, I'm getting ahead of myself, minus 3 to give us negative 4. So when x is 1, y is negative 4. Does that make sense? 1, negative 4, yes, it does. And there we have it. We satisfied all of the requirements they were asking for. And with that said, we are done. Study, practice, that's how we get better, and I'll see you next time.